Hello everyone and welcome. So what I want to do in the second part of this lecture is go over a number of different applications of Taylor series to mathematics, to physics, to various different interesting applications that we can directly do with Taylor series. I'm definitely not going to be able to cover all of the applications in this lecture video, but I'll hopefully be able to give you a taste of where these things come up in mathematics, and also where they come up in other areas of applications. And so what I want to do right now is start by reviewing one of the really important examples I went over in the previous part of this lecture, just to kind of do a little recap. And this is actually has a name. It's called the Binomial Series. And I'm going to use u as my variable. I used x as my variable when I derived it, but this was the series 1 plus u to the alpha is equal to 1 plus alpha times u plus alpha times alpha minus 1 over 2 times u squared plus alpha times alpha minus 1 times alpha minus 2 over 3 factorial, or 6, times u cubed, and so on and so forth, all the way up to alpha times alpha minus 1 times alpha minus n, alpha minus k plus 1. I'm going to use k as the general index, over k factorial times u to the k. And this continues on to infinity. It's an infinite sum. This equality is valid when the absolute value of u is less than 1. So 1 is the radius of convergence for this series, and that means the interval of convergence is for u from -1 to 1. And one of the nice things that we can do is actually write this down in a closed form notation, using just a little bit of a definition. So I'm going to define this new notation. Sometimes called the choose notation. Alpha choose 0 is 1. Alpha choose 1 is alpha. Alpha choose 2 is alpha times alpha minus 1 and hopefully you're seeing the pattern here. Each one of these is going to be the value of the Taylor series coefficient for the kth term in this infinite series. So then we said for k greater than or equal to 3, alpha choose k is equal to the kth term, the kth coefficient of this expansion, which is alpha times alpha minus 1 times alpha minus 2, all the way up to alpha minus k plus 1 over k factorial. And what's really neat now is that we can go through and directly write down the closed form expression for this Taylor series expansion, for this sum, as the summation from k equals 0 to infinity of alpha choose k times u to the k. And this is really just a notational trick here to kind of use this closed form expression, and it is very, very helpful and something that you commonly see when you see binomial series done out in applications. One of the binomial series that we're going to use today in one of our examples that I derived, and I showed you how to apply this formula for in the previous part of the lecture, was 1 plus u to the 1/2. The binomial series with alpha equals 1/2. And you'll remember that we ended up showing that this is the same thing as 1 plus 1/2 times u minus 1/8 times u squared plus 1/16 times u cubed, and so on and so forth. So this is going to be a very important series that we're going to use a little bit later on in this lecture. And for any binomial series, we have the radius of convergence is 1, so this is only valid when u is strictly less than 1. So for the next part of this lecture, what I want to do is go over a number of different applications of using the Taylor series to do various things in mathematics and also in other areas of applications. And the first couple examples that I'm going to show is how to simplify evaluating limits. And this is going to be without using L'Hopital's rule. And I think the best way of showing this is to just go through and do some examples that should hopefully be familiar to you. I'll choose a couple different examples, specifically, from the first midterm exam. The first example that we went over was the midterm was the limit as x goes to 0 of x times sine of x over 1 minus cosine of x. And on the exam, you were asked to use L'Hopital's rule to show what this limit is. But I'm going to show you a different way of going about getting this limit using Taylor series. So this is going to be the same thing as the limit as x goes to 0 of x times the Taylor series expansion for the sine function, which I will just write out term by term here to make things look a little bit nicer, a little bit easier. You can use the summation formula as well, but I'm going to go through and just do this in terms of the non-explicit formula. So sine of x Taylor series is going to be x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and so on and so forth. And then in the denominator, we have 1 minus cosine of x. The Taylor series for cosine of x, you'll remember, is 1 plus 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and so on and so forth. And at first you might think, oh, well, we're kind of overcomplicating things a little bit here, but we're really not. We're getting a very, very nice result here. If we kind of simplify this and then take the limit. First, I'll factor an x out of this series right here, so the sine series. So this is going to become x squared times 1 minus x squared over 3 factorial plus x to the 5th or x to the 4th over 5 factorial minus x to the 6th over 7 factorial, and so on and so forth. And this is going to be divided by, well, first off, 1 minus 1 is 0, and this negative sign will distribute through and turn this into positive, this into negative, this into positive, this into negative, and so on and so forth. And lastly, we can factor out an x squared from each one of the remaining terms in this series. This is going to be x squared times positive 1 over 2 factorial, which is 1/2, minus x squared over 4 factorial plus x to the 4th over 6 factorial minus the x term, and so on and so forth. And we get a nice cancellation here between the x squareds. And so this becomes the limit as x goes to 0 of this numerator divided by this denominator. And hopefully you can see the magic of what's happened here. This is the numerator limit and the denominator limit exist. The numerator limit is going to be 1 minus 0 plus 0 minus 0, and so on and so forth to infinity. While the denominator limit is going to be 1/2 minus 0 plus 0 minus 0 all the way to infinity, which is the same thing as 1 over 1/2, or 2, which is the correct value of this limit that you would get if you use L'Hopital's rule. So it's arguable whether this is a better method than L'Hopital's rule or not, but for more complicated functions, it's certainly a better method. For this function, it takes about the same number of steps to write out the answer, because you have to do 2 applications of L'Hopital's rule if you want to find this limit. But for more complicated type functions, this method of Taylor series expansion is much faster. And I just want to make a note here, right? It's important to note that these calculations that we've done are valid because the radius of convergence of both of these series is infinite, as we showed when we derived the Taylor series for cosine and sine. So really, because of this is a very nice property, any limit that you go to try and evaluate, you can use the method like this. And this is a very, very powerful tool for us. In the next example, we'll see that we can even do this if we have a finite radius of convergence and we're taking a limit inside of that radius of convergence. So the radius of convergence doesn't have to be infinity to use this right here, but it certainly helps in terms of just knowing that, say for the sine series, you can always replace sine of x with this infinite series and cosine of x with this for any value of x. In general, you have to be very careful that the value is inside the radius of convergence, but for these series, they're very nice. So let's do one more example of this. I'm going to take another example from the first exam because those solutions are posted, and hopefully you've seen the solutions to each one of these problems using L'Hopital's rule. So the next example will be the limit as x goes to positive infinity of the square root of x squared plus 7x minus the square root of x squared, which yields an infinity minus infinity indeterminate form. So we know how to evaluate this using the conjugate and L'Hopital's rule. We've seen that. Just like for this example, this is in indeterminate form. It's a 0 over 0 indeterminate form. But so this one is an infinity minus infinity indeterminate form, and what we're going to try and do is go through and figure out what this limit is using Taylor series expansions. And in order to do that, we have to rewrite this problem a little bit. I'm going to note here that x is positive, so I can rewrite the square root of x squared as being just equal to x. And I can also rewrite the square root of x squared plus 7x by factoring out the x squared, which will give me x times the square root of 1 plus 7 over x. So the limit that we're trying to evaluate here is the same thing as when I plug both of these in to right here and factor out an x. It'll be x times the square root of 1 plus 7 over x minus 1. And at first, you might not see this, but 1 plus the square root of 7 over x, the square root of 1 plus 7 over x is in a very nice form for us to apply the binomial series expansion with 1/2 in the exponent. Specifically, if I make the substitution of u equal to 7 over x, this limit expression becomes the limit as u goes to 0 from the positive of x, which is 7 over x, or 7 over u, times 1 plus u to the power 1/2 minus 1. And 1 plus u to the 1/2 is directly in the proper form for applying the binomial series expansion. Now, u is going to 0 from the positive because x is going to positive infinity, which means 7 over x is going to 0, or u is going to 0. And this is kind of key here because this means that when we evaluate this limit, as we get closer and closer to u equals 0, u is going to be strictly less than 1 as we evaluate this limit. And this means that if we kind of go back a little bit and directly pull our binomial series expansion for 1 plus u to the 1/2, we can directly substitute this expansion into our limit. So in for 1 plus u to the 1/2. And so this limit will be a limit as u goes to 0 from the positive of this infinite series minus 1 divided by u times 7. We can't forget about the 7 in the numerator, which looks a little bit complicated, but it's not too bad. We have a 1 right here, the first term in our binomial series, which gets canceled by this subtraction of 1 right here. Not only that, I can pull the 7 out from this limit process because it's just a constant. I can also factor a u out from every single term in this series. So the numerator is going to become u times 1/2 minus 1/8 times u squared, with a u factored out, becomes u plus 1/16 times u cubed with a u factored out. This becomes u squared, and so on and so forth, infinitely many times. And this is going to be divided by u still. You get a nice cancellation, and we have an infinite series that we can directly evaluate the limit of. This is going to be 7 times (1/2) minus 1/8 times 0, which is 0, plus 1/16 times 0 squared, which is 0, and so on and so forth for every other term in the series. So all the terms are 0, which gives us the value of 7 times 1/2, or 7 over 2, as the value of this limit. So again, it's definitely arguable whether this is the best method for calculating the limit, but it's certainly a very neat, very useful tool that you now have in your toolbox for calculating limits. And for many complicated functions, this actually is the fastest way of computing the limit. So let's look at another application. This is going to be a little bit outside of mathematics in the world of physics. Specifically, you can think of it also as an example from applied mathematics, or waves and oscillations. And this is something that you might see in a differential equations class. I'm not going to derive the formula, but if you say have a spring that's attached to some object and it has some mass, the formula for the motion of the spring, we'll say x of t, can be given by the following relationship. It's actually a differential equation from Newton's laws, and when you solve that differential equation, you get the following expression. This mass m is, we're going to assume it's immersed in some sort of fluid or gas, right, that creates a damping effect that's described by some constant b, where b is negative. And we're also going to assume that this omega is the frequency of the mass motion going back and forth. Each of these things can be described in terms of the given mathematical model and physical constants, but the main idea is that when you go through and solve for the motion of the mass, you'll get that the motion of the mass is of the form a, where a is the initial displacement of the mass at time 0 times e to the negative, or e to the bt, times cosine of omega t. And this is a very, gives you kind of a very realistic picture of the motion of a mass. If you kind of look at the graph of x of t as a function of time, you have that the initial location of the mass is here at A, and then as the mass oscillates, or as you kind of let it go from A, it oscillates up and down, but this oscillation decreases exponentially as time goes to infinity. So this is what x of t looks like as a function of t. And if you change the omega value, you get a different frequency of this signal. You also, if you change the b value, you get faster or slower damping of the mass itself. So like I said, I'm not going to show where this equation comes from here. That would be something that you would see in a differential equations class in mathematics, or a waves and oscillations class in physics. But what's kind of neat, right, is that one of the ways of kind of looking at this function, if we know this is the case, we can go through and actually get the Taylor series expansion for x of t using what we know. We know that the exponential function, e to the b times t, that is going to be the sum from k equals 0 to infinity of 1 over k factorial times bt to the k. And this series has to be multiplied by cosine of omega t, which has the Taylor series expansion n from 0 to infinity, the summation of n from 0 to infinity of negative 1 to the n. I'll make myself some extra space right here, over 2n factorial times omega t to the power 2n. And what's very neat here is that we can go through and re-express this as a times, this is going to be 1 over 0 factorial bt to the 0, so it'll be 1. The next term is going to be k equals 1, so this will just be b times t. plus the next term, which is going to be k equals 2. So this is going to be b squared over 2 factorial, which is 2 times t squared, plus the next term, which will be b cubed over 3 factorial, which is 6 times t cubed, all the way to infinity. And then this series right here will be when n equals 0, you're going to have negative 1 to the 0 over 0 factorial times this to the 0, which is 1. And then you're going to have negative 1 to the n, or negative 1 to the 1, so it's going to be negative 1 over 2 times 1 factorial, which is 2. And then you're also going to have omega to the 2n, so it's omega squared over 2 times t squared, and then plus negative 1 to the power 2, which will be positive, divided by 4 factorial, so it's division by 4 factorial, and then you'll have omega to the 2 times 2, which is 4, and then t to the 4, and so on and so forth. And I'm not going to go through and do this, but we know how to multiply series. We can multiply these power series together, and this will give us the actual Taylor series for x of t. Look at c naught plus c1 times t squared plus c2 times t cubed plus c3 times t to the 4th, and so on and so forth. Where each of these coefficients, c naught, c1, c2, c3, are, the nth coefficient here is the nth derivative of the function at the origin, or at the initial starting point, divided by n factorial. Put another way, the nth derivative at the origin is equal to n factorial times cn. So for a given n value, the Taylor series coefficient is giving you information about the derivative of motion of this mass at the origin, at the initial condition, which is super useful, and this is a very neat application, I think, of how you can kind of use Taylor series even from a relatively basic example from ordinary differential equations or waves and oscillations. This is very neat. Another really very neat example comes when we go to try and approximate the value of a given integral. So one of the big applications here is another mathematical application, is approximating of a definite integral. We've already seen how useful power series and Taylor series are for indefinite integrals using term-by-term integration, but it turns out we can also use this idea for definite integrals. So suppose that we have some function f of x, and within some radius of convergence around some point x naught, f of x is equal to the Taylor series expansion, say, from n equals 0 to infinity of Cn times x minus x naught to the power n. Well, we know that we can do term-by-term integration, and because of this, we know that the indefinite integral from a to b of f of x can be directly found. Now we have a little bit of a condition here that has to be true. We can only do term-by-term integration if the endpoints of the integral are inside the interval of convergence. So the interval of convergence, remember, is x naught minus r to x naught plus r. So a and b, the interval that we're going to integrate over, must be inside this interval. That's super important if you're going to do this. But if we have this, then we know that the integral from a to b of this function f of x is just going to be the term-by-term integral of the series, which will be Cn over n plus 1 times, this will be the antiderivative of x minus x naught to the n, which is 1 over n plus 1 times x minus x naught to the n plus 1, evaluated from the upper bound of b to the lower bound of a. Or the integral from a to b of f of x dx will be exactly equal to the infinite summation from n equals 0 to infinity of, this is going to be Cn over n plus 1 times b and a plugged into our function right here. So this would be b minus x naught to the n plus 1 minus a minus x naught to the n plus 1, which is an infinite series of values ak, or an, we'll say, that gets progressively closer and closer and closer as we add this sum up to the actual value of the definite integral from a to b of the function f of x. So this is a super neat application, and what I want to do is illustrate how important this is with an example from probability theory. This is called the standard normal distribution. So without defining what a probability distribution is, because this class is not a probability and statistics class, I'm just going to introduce the following function. The function f of x is equal to 1 over the square root of 2 pi times e to the negative x squared over 2. This function looks very nice if we graph out what it looks like on the xy axes. So if we take a look here, the x-axis, the y-axis, this curve is directly what's called the bell curve. So it looks the graph of it looks kind of like a bell. And this 1 over 2 pi, square root of 2 pi right here, is what's called a normalization constant. Because if you just take the integral of the function e to the negative x squared over 2, the improper integral from negative infinity to positive infinity, the area under this curve, or that improper integral, is actually equal to 2 pi. So one of the very important things that we need for probability distributions is to guarantee that the integral under the probability distribution always integrates to 1 when you integrate it over the entire real number line, from negative infinity to positive infinity. And this is, in some sense, the same thing as saying the probability of something happening must be equal to 1. Right? Something must happen. So I don't want to get into this too much, but this is why there's a coefficient of 1 over 2 pi, square root of 2 pi here. When you take your Calc 4 class, you'll actually see how to find the integral of this function itself. And it actually involves what's called double integration, which is a very important tool from multivariable calculus. So I won't be getting into that here. But what's interesting about this function is that it's not easy to integrate. If you go through and try and say, take the definite integral of this function, or just the antiderivative of this function, you can actually prove that there's no closed form antiderivative of this function. You can't express it in terms of nice, simple functions. And the problem here is that if you have, like, say, an interval, we'll say from negative 1 to 1, the definite integral of this function is very, very important in probability theory, because this represents, or I should say, the area under a given interval in probability theory is exactly the probability that a random variable will fall between the two endpoints of the interval. So I'm just going to use negative 1 and 1 here to illustrate this example. But the definite integral of this function, the normal distribution, from negative 1 to 1, we need this value if we want the value of the probability that a normally distributed random variable falls between negative 1 and 1. So the problem here is figuring this out, because there is no nice closed form solution for the antiderivative of this function. And so when we go to evaluate the definite integral from negative 1 to 1 of 1 over the square root of 2 pi times e to the negative x squared over 2, we come up with a problem here, because there's no nice way of doing this antiderivative of this function using the standard method that we know from Calculus 2. So the question is what to do. How do we evaluate this? And before what I just talked about, it might have been unclear what to do, but what you can hopefully see is that if we can find a Taylor series expansion for the function e to the negative x squared over 2, we can just plug this Taylor series expansion in here and integrate term by term to get an infinite series that converges to whatever the value this is. So the first step here is noticing that and then saying, well, we know that e to the u is the summation from k equals 0 to infinity of 1 over k factorial times x to the k. Or, not x, I want to use a u here because I'm going to be substituting in. So then e to the negative x squared over 2, the same thing as e to the u, with u equal to negative x squared over 2. So this is going to be the summation from k equals 0 to infinity of 1 over k factorial times negative x squared over 2 to the k, or the summation from k equals 0 to infinity of -1 to the k over k factorial times 2 to the k times x squared to the k, which is x to the 2k. And so we have now a very nice series for e to the negative x squared over 2, which we can directly plug in to this definite integral. It's going to be 1 over the square root of 2 pi times the definite integral from -1 to 1 of this infinite series, which we know will definitively be the term-by-term integral of this entire thing. This is going to be the summation from k equals 0 to infinity of -1 to the k over k factorial times 2 to the k times the integral from -1 to 1 of x to the 2k dx. This integral. This is going to be 1 over the square root of 2 pi times the summation from k equals 0 to infinity of -1 to the k over k factorial times 2 to the k, and this antiderivative is going to be x to the 2k plus 1 over 2k plus 1 evaluated from 1 to -1. This is just the integral of this function of x. This is then going to be 1 over the square root of 2 pi times the infinite summation from k equals 0 to infinity of -1 to the k over k factorial times 2 to the k, and this will just be times then 1 over 2k plus 1 then times 1 to the 2k plus 1 minus -1 to the 2k plus 1. And this simplifies even further when you kind of simplify this 1 minus -1 to the 2k plus 1. So 1 to the 2k plus 1 is always 1. -1 to the 2k plus 1 is the same thing as 1 minus -1 times -1 to the 2k. -1 to the 2k is always 1, because it's the same thing as -1 squared to the k. And negative times -1 is positive. So this is just, this entire thing is just the same thing as 1 plus 1, or 2. And so, our answer is 1 over the root 2 pi times the sum from k equals 0 to infinity of negative 1 to the k times 2 over k factorial times 2 to the k times 2k plus 1. And this is an infinite series expression for the integral from negative 1 to 1 of this function f of x. So this value, whatever the series converges to, is exactly the probability that a random variable will fall between negative 1 and 1. I think this is a very cool example. And all of these manipulations are valid because the Taylor series radius of convergence for this function is positive infinity. Right? You can go through and directly show that. So this is very neat. In fact, if you go through and approximate the value using some other method, the value is approximately equal to 0.682689, and it actually only takes the first 7 sums, or the first 8 sums. So from when n is 0, if you consider this summation, if this is your ak right here, so you consider the value of 1 over the square root of 2 pi times the sum from k equals 0 to 7 of this ak. This value is approximately equal to 0.682689, which is 6 degrees of decimal degrees of accuracy. So you'd say that the probability that the given randomly distributed random variable falls between negative 1 and 1 is about probability of about 0.682 or 68%. The final example application that I want to show is probably one of my favorite applications of Taylor series in modern mathematics. And this is called Eulers Equation. And simply put, this is a very, very nice, amazing, actually, relationship between the exponential function, the cosine function, the sine function, and what's called the imaginary unit, or I. So I is called the imaginary unit, and it's a mathematical quantity that satisfies I squared is equal to negative 1. Sometimes it's written as the imaginary unit, but there's nothing imaginary about it. It turns out to be a very well-defined thing. And there's actually a whole branch of calculus called complex variables that deals with the calculus of functions of complex variables. I won't be getting into any of that here. Basically, the only thing that you need to know about I is that it's this it's a complex number, actually it's an imaginary number, and when you square it, you get negative 1. Right, so no real number has this this property, but I does have this property. I'll write this a little bit more, less like a C, more like an I. So Euler's equation is the equation that e to the I times theta. This is for any real value theta, so any real number theta, e to the I times theta is equal to cosine of theta plus I times sine of theta. And believe it or not, this equation is used so much in modern physics, modern engineering, from electrical engineering to modern physics, phasers, all sorts of areas. So this is a fundamental mathematical relationship that's very, very special. And we can show this relatively easily using Taylor series. We know that the exponential function, the cosine function, and sine function all have Taylor series with a radius of convergence that is infinite. The only thing that's a little bit, you have to take my word for it here, is that the radius of convergence for the exponential also extends to complex quantities. This is something that happens. So we know that e to the u is the summation from k equals 0 to infinity of 1 over k factorial times u to the k. So e to the I times theta is going to be the summation from k equals 0 to infinity of 1 over k factorial times I times theta to the k, which is the same thing as the summation from k equals 0 to infinity of I to the k over k factorial times theta to the k. And this is where the magic happens when we consider what I to the k is for various values of k. Well, when k is 0, it's a well-known property of complex numbers that complex number to the power 0 is just the real number 1. When k is 1, I to the 1 is just I. When k is 2, I squared is going to be negative 1. When k is 3, I cubed will end up being I times I times I, or negative 1 times I, which is negative I. When k equals 4, we have that I to the 4 will be negative I times I, which will be negative I squared, or positive 1. And then this process is going to repeat itself in a loop as you continue on to higher and higher degrees of k. And sometimes this can help if we can go through and just write out what this series is. Right? This is going to be I to the 0 over 0 factorial times theta to the 0 plus I to the 1 over 1 factorial times theta to the 1 plus I squared over 2 factorial times theta squared plus I cubed over 3 factorial times theta cubed plus I to the 4th over 4 factorial times theta to the 4th, and so on and so forth. And using the fact that these powers of I simplify very nicely, we have that this is going to be 1, this is going to be plus theta times I, or say I times theta, and then we'll have I squared is minus 1 over 2 factorial times theta squared, and we'll have minus I over 3 factorial times theta cubed plus I to the 4th, which is just 1, so 1 over 4 factorial times times theta to the fourth. And this looping process with the coefficients continues all the way to infinity. Because this series is absolutely convergent, we can rearrange terms. I'm going to pull all of the real values together. 1 minus theta squared over 2 factorial plus theta to the fourth over 4 factorial, and so on and so forth. So all the even values of the exponent I'm going to pull together and add them. And all of the imaginary, or the things with an I on them, I'm going to pull together, and I can factor out the I to get theta minus theta cubed over 3 factorial. Next term up here will be theta to the fifth over 5 factorial, and so on and so forth. And we can immediately recognize this as the Taylor series for cosine of theta, and this as the Taylor series for sine of theta. And there you have it. You've shown Euler's equation. E to the I theta is equal to cosine of theta plus I times sine of theta. This is a super useful theorem. And it also gives what's called Euler's identity, which is one of the most beautiful equations in mathematics. If we plug in pi for theta here, we have that e to the I pi is equal to cosine of pi, which is -1, plus I times sine of pi, which is 0. So this equation is the same thing as the equation 1 plus e to the I times pi is equal to 0, which is called Euler's identity and is regarded as one of the most beautiful equations in mathematics because it connects so many different fundamental numbers, basic fundamental numbers from different areas of mathematics, specifically 0 and 1, which are probably the two most important natural numbers, e and pi, which are the two most important real numbers, and then the imaginary unit I, which is the most important complex number. So this is probably one of the coolest identities in mathematics. Definitely one of the most beautiful identities in mathematics. But that will be all for lecture today. Thank you very much for tuning in. I hope you learned something and had a great day.